This is the final presentation for the Powell Lacrosse Handle Flex Testing Group. This project was completed at Clark University for the Test Engineering course, also known as ME401. Our group members include Riley Kuzma, Molly DiCaprio, Rachel Williams, and Thomas Dunbar.
To give some background on Powell Lacrosse, they're a lacrosse equipment company based out of Champion, New York, which is just east of Syracuse. The Powell brothers are very decorated lacrosse players that played both Division I lacrosse and went on to play professionally. After their playing days were over, they wanted to continue to show their love and appreciation for the game, so they launched their company in hopes to improve the game for all athletes who have come after them. Since our groupmate Riley has been in previous contact with their company and she shares the same passion for the sport, we decided to use their shafts to test for our project. Prior to us creating our test plan, we performed some research and found two other companies that completed similar testing to test the strength of lacrosse shafts. Tomahawk Lacrosse did flex testing, however, they did not use a load frame like we did for our testing. ECD Lacrosse was another company we found under a case study written by MTS Systems. For their testing, they used an MTS system load frame to complete 3-point bending test, as you can see by the photo provided in the slide. This photo is the only picture we had found of a test setup as similar to what we are trying to achieve. We were given information from Powell prior to testing, which also allowed us to slightly change our approach compared to the two companies' testing that I have just mentioned. Powell told us that their shafts fail most frequently on the longer sides of the octagonal shape. Given this information, we were mindful on how we loaded the shaft onto our fixture and assured we had appropriate orientation prior to testing. It is important to note that there is no current testing standards in place for testing these lacrosse shafts, which added some difficulty during our planning and methods phases.
Powell was able to provide us with specific information about their handles. This included the dimensions of the cross section for the handle, which is shown in the image on the left. This was helpful when designing the handle in SolidWorks. We then used the SolidWorks drawing to get the moment of inertia for later calculations. We know that one of the shafts was scandium titanium alloy and the other was a 7UI. Powell was able to provide the specifications for the 7UI material, and this is shown in the image on the right. Our test objective is to test continuous force to see at what force the Powell cross shaft handles will break. This is important because it will provide Powell with crucial information about their handles. Since they are a relatively new company, they don't have any technical documents. Our final report can be one of the first technical documents they have. This will not only help them improve their handles in the future, but could also be used to help their company grow. It's also important to note that since we found that there is no specific standard for our test, we decided to base our test generally on the standard for ASTM 290 guided bending with no die test. The general layout for this test standard is shown on the image in this slide. Our test plan went through many revisions before we were able to finalize it. Half of the battle was finding a load cell that would provide enough force to possibly break the handles. After several discussions with Dr. Hoover and our TA Medi, we found that using the load frame in the lab in Camp 215 would be the best for our compressive load testing. An important part of the test was the setup. We had to place and secure the fixture and handles properly, which is explained more in the procedure in the following slides. We secured the handles and fixtures with a string from the makerspace. The picture here shows the initial setup with the fixture and handle secured before the protective guard was put in place. The specific machine used was an Instron 5900, which was connected to a Blue Hill 3 testing software. When we started testing, we ran into a problem. The computer connected to the load frame did not have the correct program installed and or it was not working properly. This delayed our testing by a few days as Dr. Hoover had to work with OIT to resolve the technical issue. Once the issue was fixed, we were able to begin our testing and set up our program in the software. Another important part of our testing was that we had to overcome several issues with the fixtures used. The picture on the left shows the original fixtures we used that we found in the ME lab. The main issue is that within the picture on the left, the rollers were way too close together. To simulate a lacrosse handle being hit, we want to have two hands far apart and then a force in the middle. The two hands are represented by the bottom two rollers. We had to take apart the fixture and reassemble it to move the fixtures to the end of the given rod. The final fixtures are shown in the image on the right. You can see how the bottom rollers are now farther apart. The top fixture has two rollers close together, and since they are so close, we can assume that there's only one roller, and therefore we have our 3-point bending test satisfied.
For our procedure, we had one for the computer system that we used, Blue Hill, where we set up a new test method and defined our end test conditions and parameters. Our other procedure is for the actual testing. So we set up the handle and the load frame as seen in the picture. We made it so that there was no room for the piece to move before the test began. Make sure all the safety guards up and the piece was tethered to the machine, and then ran the test with the baseline method for the first 3 trials. Then for the last 2 trials, we used a failure method where we increased the end condition to more deflection to see how much force it would take to get to that amount of deflection.
For equipment, we used the load cell, which is an Instron 5900, with as well as brass bushings we ordered from McMaster Car. And we also altered the fixtures for the load frame and as well as the computer. We used 2 different lacrosse shafts from Powell. The Bloodline Pro shaft, which is made of scandium and titanium alloy, and the Switchback shaft, which is 7UI. And the costs really of this project were the brass bushings, one for $9.95 each, and then the oil embedded sleeve bearings, which were $21 each.
Using the RAMP risk assessment format, we were able to identify all possible risks associated with our project testing. Since we are using a load cell, there is enhanced risk of injury, such as being crushed underneath the load frame. The prevention put in place is to always announce and make others aware that the load cell is on, and this includes any additional personnel who enter the laboratory during testing. Since we are adding hundreds of pounds of force to these metal shafts, there is a risk that at failure the shaft could turn into a dangerous projectile since it is under extreme stress and force. To mitigate this, we secured each end of the shaft to the load frame with a string, and we attached a large shield to the front of the load frame as well. The way our fixture was designed, we were not able to attach it properly to the top of the load frame, meaning the fixture had to be pressed firmly against the shaft prior to testing so it could be held in place. This caused a risk that the fixture would be falling from the load frame if the shaft were to fail. To prevent this, we also secured the fixture on both sides of the load frame with a string similar to how we secured the shaft.
As far as our results go, we have the switchback data plots, which have our raw data, which is what was outputted into the computer system. When we were doing all of the tests, this one specifically is for our 5th trial, where we went to 19 millimeters of deflection. And we also have our load versus time, which shows that for the majority of the time, it's a linear increase in load. And then after we reached a certain point, it reached a maximum load, and then the test piece started to deform where the load then decreased. Our bending moment at the application point of the force at one of the upper fixtures is linear throughout the entire trial. And then we have the flexural stress versus strain curve, which you can see is mostly linear. And then we actually reach past the elastic period of the material and move towards the plastic period. The deflection at the end of the final trial is shown in the bottom center graph, which you can see it should be almost a perfect parabola, besides the middle point where the upper fixtures were touching the test piece. And then we have the bending moment versus the position on the handle for the end of the trial. We have very similar looking graphs for our Bloodline Pro handle. The only difference is that there's about 100 newtons less on the raw data, and then everything else pretty much describes the same type of relationship. A linear bending moment, flexural strain is linear for the majority of the trial, and then kind of tops off and then fades away as the piece deforms. And similar deflection and bending moments as we use the same test parameters. On this slide, we just have tabulated results. So we have the load applied at the first, second, and third end condition of each of the types of trials we ran. As you can see, there's only about 100 Newton, 200 Newton difference between the two. Very similar as far as the rest of the results go. The maximum load applied is where that graph topped off before. Then we have the maximum stress and strain that each piece incurred. The final angle of deflection is about 2 degrees. It was difficult to measure because of the shape of the handle. And then where the elastic period is estimated to end is the bottom result of about 12 millimeters and change for both. And then the loads differ again by about 200 newtons. With these results, we concluded that both materials can withstand similar forces, and they also deform the same way, where they reach a maximum load and then where they can bend, and then the material actually starts to deform on one of the sides of the octagon, which happens to be the side that the fixture is pressing down on. So we'd assumed that if we went to full ductile fracture and failure, that it would break on the top half where there's compression before the bottom half breaks in tension. Moving forward with our project, our next steps would be to use this information to design a new shape of a lacrosse handle, whether that be adding material in certain places or taking it away in others. And we would use these results to compare how they would deform as well as how much force it would take for them to fail ultimately or with past the elastic period. As always, all of this work will go to improve the game of lacrosse as well as all the equipment that is used. In the future, we'll follow up with Powell Lacrosse and give them our results as well as the conclusions that we've drawn from them, and then move forward with either testing more of their materials or looking to design something new.
We had the opportunity to work with many qualified people throughout the duration of our project. They helped us tremendously, and we could have not completed what we did without them. Those who helped contribute to this project are listed on the slide. Powell was a huge sponsor with providing us with lacrosse handles and information about their shafts. Dr. Hoover was our instructor for the course, and he was able to provide us with constant guidance to be successful with our project. Mehdi was assigned as our TA, and he was a tremendous help. He was a great addition to our group and helped us to solve many problems we faced.